Hello, this is a video to go through P2 Topic 3, which is Motion and Forces on the Edexcel GCSE. So as with my other videos, I'll quickly go through each of these levels here, just to make sure that you know what you sort of need to do each level, and then I'll go through all the content within this topic. So the situation we're discussing is a ball bearing falling through honey. It reaches terminal velocity. So remember, watch this part of it if you're quite comfortable with the topic. If you're not, then watch the rest of the video to make sure that you understand. Right, okay, so to start off with, let's look at some of these grades here. So we're going to explain how it actually reaches terminal velocity using the idea of forces in motion. You can use some diagrams if you want. So first we'll list the forces acting on the ball bearing. Okay, so if I bring my pen over. Okay, so if we've got a ball bearing and it's falling through honey, we're going to have the force of weight acting down. Now weight is essentially mass times by gravity, so it's the mass of this ball bearing times by the gravitational attraction downwards, which on Earth is approximately 10. Acting upwards is actually two forces if it's moving or at terminal velocity. That's up thrust, that's because that ball bearing takes up some space. But the main one for GCSE that you need to know is air resistance. Up thrust is not so much of an issue at GCSE, but air resistance is. Because we're in honey, it's technically fluid resistance, but if it's in the air, it will be air resistance. Draw a free body force diagram to show the forces acting. So if I just call that FR, so we know it's fluid resistance, but it could be air resistance if it was in the air. So draw a free body force diagram to show the forces acting on the ball bearing. There we go, that's what we call a free body force diagram. Remember, the arrows need to touch the object. Technically they should be from the centre of mass of the object, so they should be coming from the middle, something like that. Well, there we go, that one there. Okay, sketch a velocity time graph of the ball bearing. So there's no scale actually required for this diagram. Okay, we just need a quick little sketch to say what we think it's going to look like. So here's our velocity time graph, velocity on this axis, time on this axis. Remember, it's going to accelerate to begin with, not accelerate less and less and less with time, and then level off. This is the bit where it reaches terminal velocity. So at the end, over here it's accelerating. Remember, the acceleration decreases due to air resistance increasing. So we've done grade E, D and C. Sketch a distance time graph to show the distance travelled by the ball bearing. Again, no scale required. This is trickier. And reflecting on this, reflecting on the sheet that I've made, I'd probably say this is slightly harder than a grade B. You've got to think carefully about what's happening. When an object's accelerating, it's going to cover more and more distance over time. So over here, because it's accelerating, it's going to end up covering more and more distance, so it curves. Like so. Over here it's going at constant speed, so it actually levels off and goes up with a constant gradient. Oops. That should be a straight line. Very poorly drawn. Bit out of practice with my graphics tablet. Okay, so there's the curve, and that over here should be a straight line. That there should be a straight line. Oops. Scroll off the page here. That should be a straight line. That's a straight line of constant speed, and there's my curve. And so my students will be taking a look out of my inability to write here. Right, next, describe how the size of the force vary on the ball bearing as it falls. Okay, so this one's pretty straightforward. If you think about the object as falling, there's a few stages. There's stage number 1 over here at the start, there's stage number 2 over here, and there's stage number 3 over here. Okay, underneath, I'm just going to do a bit of writing which sort of explains each of these stages. So the first one, weight is the only force acting. So to begin with, there's no air resistance, there's only weight. Okay, so there's only the weight over here. There's no fluid resistance, no air resistance. That's because it's just about to start moving. This fluid resistance only comes about when there's moving. Okay, so as the object, in this case the ball bearing, starts to move, fluid resistance or air resistance is also present. Right, you've got to say what's happening to the motion. Okay, because it's weight acting down only, it accelerates down. That's the motion force. Next, well, that acceleration increases fluid resistance or air resistance. So that's what's happening in stage 2. That's what is less acceleration happening. It should really be leveling off. You can see it over here. It just starts to level off. Less fluid resistance. Over here it completely levels off, and that's when weight is equal to fluid resistance or air resistance. Yes. Okay, so that's where the forces are equal. That's terminal velocity, when the forces on an object are balanced. Right. Explain how the so if we're describing how the sizes of the forces vary, weight stays the same, but fluid resistance or air resistance increases. And explain how we can use a so yeah, that's it. Next, explain how the ball bearing reaches terminal velocity. So that's what we've done over here. And explain how we can use the distance time graph to calculate the terminal velocity, and how we can use that should say the velocity time graph. So let's do that correction now. I should say the velocity time graph. To calculate the total distance travelled. So the distance time graph to calculate terminal velocity, that's easy. That's just a gradient of this graph. And I'll be going through later on how to find the gradient. It's essentially a change in y divided by change in x. Remember, if it's for this graph, only the linear region, only the straight line. And if it's how we can use a velocity time graph to calculate the distance travelled, so here's my velocity time graph, it's the area under the graph. Okay, so we've been through the assessed sheet there. I just want to bring up, there we go, the notes document. So again, I'm just going to go through this bit by bit. As per usual, I have my highlighter at the ready. Let's just have to sheet response. There we go. There we go. Right. Okay. So vectors. First thing you need to know is about vectors. Vectors have both direction and magnitude. What we mean by that is that they have size and direction. Okay, so a force is a vector because it has a size of force, that's 4 newtons, and a direction to the left. Each of these are vectors. There's one more vector, which I haven't mentioned in this list, which has come into recent papers, and that's momentum. So momentum is also a vector. Right, so let's get straight into distance time graphs. If you have a distance time graph, this area over here is a constant speed because it's a straight line that's going up diagonally. This bit's stationary because you can see the distance isn't changing. You can see the equation here, speed equals distance over time. The gradient of the distance time graph tells you the speed the object is travelling at. So to figure out the gradient, you need to know your change in y divided by your change in x. So if I grab the pen tool, say this number here was 3 and this number here was 10. I haven't chosen nice numbers there. And say this number here was 2 and this number here was 4. Then this change over here is 7. This has gone from 3 to 10. My change in x is about 2. This has gone from 2 to 4. So my gradient, the slope, y divided by x, is 7 divided by 2, which equals 3.5. So as this is distance over time, that's going to be 3.5 meters per second. So remember, speed just tells you how fast it's going. Velocity will also tell you the direction. If you want to know how much something's accelerating, okay, we use the equation acceleration equals change in velocity divided by time. Quite often, they like to use the letters v and u, where v is how fast it's going at the end, the final velocity, and u is how fast it's going at the start. So here we have velocity time graph. You can see over here, we've got velocity on this axis and time on this axis. You've got constant speed now, this time when it's level. And you've got an acceleration happening over here when it's diagonal. So it's changed from a distance time graph. That was previously constant speed for distance time. For a velocity time graph, that's an acceleration. This is a constant speed now because you can see the velocity is not changing. This acceleration is greater because it has a larger gradient. Again, finding out the gradient in this one tells you something different. It's the acceleration this time. The gradient of a velocity time graph tells you the acceleration. The area under a velocity time graph tells you the distance travelled. So you can see the area under a graph here. So with a graph, you split it into two shapes that make it up, and you can figure out the area under that graph. If it's a triangle, you half base times height. Okay, the area of that triangle is half base times height. And this is a rectangle, so that's just base times height. You add those two areas together, that's the total distance travelled. Okay, so I know I've gone through it quite quickly, but it's an area that I feel that people that are quite strong in the maths do quite well on. So feel free to go over that again if you feel you need to brush up on the math side of P2. Think about that. I will try to make a video about rearranging equations and using triangles to help you rearrange equations as well. So forces. Apologies, just dropped my phone. Don't worry, it's not broken. So when it comes to forces, we like to draw free body force diagrams. So this is kind of like a free body force diagram. It's not the best. The arrows should be touching the object. They should be coming from the centre of mass, but they show the forces acting on an object. If there's several forces, so like two forces acting on an object, we like to combine them. So you've got two forces acting here. We like to combine them into one, and we call that idea a resultant force. So if the object is stationary, or the resultant force is 0, and the object remains stationary. If the object is stationary and the resultant force is not 0, then it accelerates in the direction of that force. So if this was stationary and now it's got a resultant force, it'll accelerate this way. Now this is a key point that people seem to not grasp quite well. So if an object is already moving and the resultant force is 0, so if there's no resultant force but it's already moving, it will keep going at the same speed in the same direction. So if this was already moving, this will accelerate now. But imagine this bit here didn't exist. So imagine this arrow is now gone. Let me change the colour to make it clear. Okay, yeah, there we go. Just colour that out. There's no arrow there. So if this was going at a constant speed of say 10 meters per second, it would carry on because there's no resultant force now acting on it. Change that back to euro. Okay, so to summarise, balanced forces lead to a constant speed, while unbalanced forces lead to an acceleration. Remember, 0 can be that constant speed. So this one over here, this top diagram here, that's going at a constant velocity. You can see the size of the arrows are the same. This one's accelerating towards the right, this car's slowing down because the resultant force is actually in the opposite direction. So look at the direction of the resultant force, and that will help you out. So this leads to an important equation known as Newton's second law. So that's force equals mass times acceleration. The biggest thing that people make mistakes with in this one, they forget that the mass is in kilograms. Please make sure the mass is in kilograms. Weight is also an important force, and as I said earlier on, weight is equal to mass times gravitational field strength, which is usually 10 on Earth, value of gravitational field strength. They'll tell you that in the exam. But mass, remember, in kilograms. In a vacuum, all objects will accelerate at the same rate due to gravity, but because of Earth's atmosphere, we're not in a vacuum, so we end up having objects reach terminal velocity. So I've explained terminal velocity, I've explained it in terms of fluid, but there's some more on it over here, so I'll go through that in a second. I just want to quickly go through the link between force, mass and acceleration experiment. Now you might have done this experiment in class. I know it's been a controlled assessment in the past, so I just want to quickly go through the key things here. You've got a mass over here that you're accelerating, you've got the acceleration for this mass over here, and you're applying a force in this direction. So there's your F, there's your M, and there's your A. Now because these are masses, people often confuse this with the mass that's being accelerated. These are not the masses that we're actually accelerating. This is going to be times by 10 to give us the force that is accelerating this mass. We can use light gates to measure the acceleration on this mass, or we can do it using a ticker timer, which you might have used in class. Ticker timers are the machines that leave little dots on a piece of paper, and you can use that to calculate acceleration. So let's quickly go through the idea of terminal velocity. So remember, it can be in any fluid, so that's a liquid or a gas. Oops. Okay, so that's any liquid or gas. So you've got a skydiver here, only weight is acting on him to begin with. He then falls further down, he's accelerating, so therefore he has air resistance. Remember, the faster he goes, the larger the air resistance. He's accelerating because there's a resultant force. There's still a resultant force here in the second picture, so he's still accelerating. And in the last picture, there's no resultant force, so he's at a constant speed, and that's called terminal velocity. Remember, look back at the start of the video for the terminal velocity graphs. That's something I quite like to ask. Remember that on these graphs, do sort of label the forces. I'm just going to give you a couple of examples on this PowerPoint slide. So if you've got your, it's not the best axes, but there we go, velocity time graph, and it's got this sort of shape on it. Okay, and then it ends up being flat there. So that's him getting up to terminal velocity, and that's him then falling and hitting the ground. Let's hope he didn't injure himself during that process. Over here, we've got weight is greater than air resistance. Over here, weight is still greater than air resistance here, but by not as much. Over here, weight is equal to air resistance, and over here, there's no forces whatsoever. So remember to map those forces onto the graph so you have an idea. So if you get a graph like this, label the forces onto it. And that finishes off our video on P2 forces and motion.